So now it's a time. So let's start the 44th ASE seminar, Advanced Supercomputing Environment. So welcome to our seminar. It's at this time. So we are now around some members from the outside. So let's talk about some of the seminar. So the history is some Professor Katagiri in the country NWSP started the series of a seminar in March 2008. And this seminar has been held regularly. When we have some domestic or international visitors to the Information Technology Center in the University of Tokyo. The other speaker is not necessary to limited to the faculty member of ITC in Tokyo. Officially, the language is not fixed, but in this case, it's English today. And the first seminar was on March 3rd in 2008. And this is some of any topics related to HPC and supercomputing. And last meeting before COVID-19, 40th on February 4th in 2020. After that, we restarted in a seminar online in February 4th, maybe 2 years later. And then went to submit in this April and the 43rd in last week. And please see some following slide to see some of our seminar. So today's guest speaker is Dr. Yuan Rang. So this similar research laboratory in Norway. Yuan is visiting Japan for ICIM 2022, maybe was last week, and some 10th International Congress in the Industrial Speech. We have his speech in the picture of that there, and it's over 5,000 people attending in the Waseda University. So I like some introduce Yuan some language. So Yuan Langes is a senior research scientist in the Similar Research Laboratory and associate professor at the University of Virginia, Norway. And he is leading interdisciplinary project in social network analysis and graph neural networks. And peer is the European high performance computing project SuperCity. And his research interests are focusing on some high performance computing using a heterogeneous architecture and parallel algorithm and sparse linear algebra and combinational science computing. And here is a seminar. First is this 5 minutes talk from the my name is Shinichi Moto from University of Tokyo, and here is the thing. So let's get started. So the first talk from the video, and his talk is from Kengo Nakajima in the Information Technology Center of the University of Tokyo, and in a similar research laboratory in Norway. So let's take the video and let's start it.
Hello, everybody. Welcome to the 44th ASE seminar. My name is Kengo Nakajima, faculty member of the Supercomputing Research Division, Information Technology Center. It is my great pleasure to host Johannes' visit to the University of Tokyo. Unfortunately, I cannot attend the seminar today. Therefore, I will briefly describe the history and the recent activities of our collaborations between University of Tokyo and Similar Research Laboratory. Our collaboration is an international project of JHPCN since 2018. JHPCN, Joint Usage Research Center for Interdisciplinary Large-Scale Information Infrastructures, is the alliance of supercomputer centers of 8 national universities in Japan. University of Tokyo is the core institute of this alliance. Main activities of JHPCN is promotion of collaborative research projects using facilities and human resources in 8 centers. Initial target of this project was optimization of the simulation code for cardiac electrophysiology developed by Shimura on Oakforest-PACS system with Intel Xeon Phi. JCHPC, Joint Center for Advanced High-Performance Computing, is a collaboration between University of Tsukuba and University of Tokyo since 2013. We introduced a big system by combining budgets of two supercomputer centers. Oakforest-PACS OFP with more than 8,000 Intel Xeon Phi is the first system of JCHPC. At the first appearance in Top 500 November 2016, it was 6th in the world and top in Japan. After retirement of K-Computer in 2019, OFP worked as the national flagship system, in fact, until operation of Fugaku starts in 2020. OFP retired in March 2022. This is a brief summary of our activities in each year. Wishtira BTX1 is our primary target system now. It is designed for integration of simulation data learning, S plus D plus L. Peak performance is 33 petaflops and aggregated memory bandwidth is 8.38 petabytes per second. The system is constructed by Fujitsu. It is a hierarchical, hybrid, and heterogeneous system with two types of node groups. Simulation nodes for HPC, Odyssey, with more than 25 petaflops is based on Fujitsu's Prime HPC FX1000 with A64FX with high bandwidth memory. And this part is the commercial version of Fugaku supercomputer. Data and learning nodes, Aquarius, a GPU cluster consisting of Intel Ice Lake and NVIDIA A100 Tensor Core with 7.2 petaflops for data analytics, AI, and machine learning workloads. Some of data and learning nodes are connected to external resources directly. It has totally 360 A100 GPUs. In our work, GPU part is also used for simulations. This is a list of the participants in 2022. Many of original members of University of Tokyo have moved to other organizations. Members of Shimura Research Laboratory are from various countries. Actually, Shinchai, co-PI of Shimura side, and I have been close friends for more than 20 years. The target of the code is simulations of cardiac electrophysiology. Millions of meshes are needed for realistic modeling of 3D geometry of heart. Therefore, large-scale parallel computers are essential. The code solves 3D nonlinear reaction diffusion equations. Operation splitting are applied. And there are two parts. PD part, partial differential equations for diffusion equations, and ODE part, ordinary differential equations for reaction equations. Cell-centered finite volume method with unstructured tetrahedral meshes are applied. The program is parallelized by MPI and OpenMP. Name of the simulator is Lynx. PD part for solving 3D diffusion equations was originally based on explicit time matching. In 2020, we started to investigate implicit time matching, where we can apply larger time steps. ODE part solves reaction equations in each cell. This part is done by embarrassingly parallel manner. This slide summarizes the activities in 2022. While we have many continuous works from 2021, we try to port our code to GPU using OpenACC and standard parallelism. This is a list of publications. Here, I describe the activities related to GPU porting. We are now preparing to introduce successor of OFP, OFP2. In order to attain maximum performance under constraint of electric power consumption, switching to accelerators such as GPU is essential in next 10 years. After February 2022, energy cost has been increasing, and the cost of electricity was doubled, while that is now stable and reducing. OFP2 will start its operation in January 2025. It consists of two types of node groups, Group A with general-purpose CPUs only, and Group B with GPUs. We continue the direction for integration of S plus D plus L. We have already decided to adopt NVIDIA's GPU, which is a H100 or its successor. Performance itself and portability of the applications in Fortran are highly evaluated. OpenACC and standard parallelism are relatively easy and suitable for existing applications by users with MPI and OpenMP. We just released RFP of OFP2. We expect peak performance of Group B is more than 100 petaflops. CPUs in Group A and Group B could be different. Moreover, we start operation of Mercury, prototype of OFP2 with 16 H100 in this October. This is the situation of OFP2 and Mercury. Let me overview the activities for porting last year. Our goal is to develop a GPU version of implicit solver using OpenACC and standard parallelism on Wisteria BDEC01 Aquarius with NVIDIA A100 GPUs. The most expensive procedure is conjugate gradient solver for large-scale linear equations. As you know, applying OpenACC and standard parallelism is very easy. Just replace directive like this way, or like this way. This page describes the strategy. Basically, we replace OpenMP part with OpenACC and standard parallelism, while matrix access is changed to column-wise structure of array manner. As for the halo exchange, we prepared special function with CUDA-aware MPI. So this function can be utilized for other applications. In the next two pages, results of best cases are shown. This is the performance of conjugate gradient solvers. Significant improvement of performance is attained by GPUs. OpenACC and standard parallelism are competitive, while standard parallelism is worse for smaller data with more GPUs. The reason is that standard parallelism cannot launch GPU kernels asynchronously. Performance of GPU is much better for larger problems. This is a relative best performance compared to that of the two Xeon CPUs. Performance improvement by GPUs is significant for larger problems. Speed up is reasonable considering the ratio of memory bandwidth because this is memory-bound applications. In this case, changes are applied to less than 4% of entire code. This is the plan for this year. We are now introducing new models for simulations. The new model is called EMI, considering extracellular space, cell membrane, and intercellular space. We need to solve PDEs for E and I, and ODEs for M. This year, we are mainly focusing on implementing this new model. Thank you very much for your attention. If you have any questions, you can talk to Johannes or leave messages to me. I hope you enjoy today's ASE seminar.
Thank you. So this is a video presentation, so it's not a Q&A. So I would like to show next talk. So next presentation is Johan Lange, our guest speaker. And the title is some transitioning scientific computation to novel AI hardware. The example of the cosmic electronic psychology simulation. So let's go outside.
Yes, thank you.
Yeah.
Yes, so I believe Kengo has already introduced the problem to a large extent. So, but first, let's just start with someone, I guess Kengo already talked about that, right? Why am I here, right? So this is essentially part of this collaboration between Simula and the University of Tokyo, which is led by Kengo Nakajima and Shinkai. And well, on that, because of me being here due to in the context of the conference, right, it felt like a good opportunity to make contact with groups that we've so far only been talking remotely. And well, I'm from Norway, or let's say I'm not originally, but my institute is in Norway. I'm working at which is essentially a country which is mostly known for fjords and waterfalls, not so much known for lots of people. So yes, it's a bit that does make a few differences, right? And these are my two affiliations: Simula Research Lab in Oslo and the University of Bergen, which is on the other side or on the other coast of the country, which is quite far away, even though it doesn't look so much on the map here. And yes, so about Simula, right? So this was already mentioned. So Simula is a government-owned and publicly funded, but privately run research lab. So it's in a sense, so the way we operate is very similar to the Department of Energy labs like Lawrence Berkeley, Oak Ridge, and so on. And except that we only do ICT, information communication technology, or computer science research. We don't do physics or similar other fundamental sciences. And well, I like to call us Norway-sized, as in we are obviously not as big as the DOE labs. So, but otherwise we operate by very similar principles. And yeah, we also like to point out that we are very international. So, I mean, technically less than half of our staff is actually from Norway, and with a lot of people coming from Europe, some from America, and also a growing portion from Asia. And we have a large number of international collaborations. I mean, these are things for national and international. So we, for example, operate or collaborate with the University of Bergen and Oslo for our PhD students. So the students work with us, but they are receiving their degrees from the University of Oslo, for example. And then we have long-running collaborations with international sites, and of course, smaller collaborations like the one here, which is more like based on personal initiatives like the ones that Shinkai and Kengo are running. And one of the more interesting things HPC-wise is, so we do not have a supercomputer like Wisteria here, but we have a so-called exascale experimental infrastructure, which is called EX3. And so this is a small machine that has a lot of different supercomputer technologies, such as Intel CPUs, ARM CPUs, AMD CPUs, AMD GPUs, NVIDIA GPUs, and also what I'm talking a little bit more today is ground core IPUs, which are AI accelerators, which are originally meant for AI, but we're talking about using them for scientific computing, right? And as you can see, the machine is not very big, but it's very heterogeneous, right? So there is really something of everything in there. What we are not doing is what you talked about earlier, right? So what we have not really been testing so far is really using multiple different architectures in the same computation. What we've been mostly using it so far is doing the same thing on different platforms and then finding out on which hardware platforms does a certain application run well, on which does it run not so well. And yeah, so what are we trying to do? Kengo has already introduced this. So this is one of the specific problems in cardiac electrophysiology. And we want to understand, is there, essentially we want to predict arrhythmia. So there is a patient's heart, and we want to understand, is this patient at risk of arrhythmia? And this is a tricky and very important medical procedure. And this is so far not very developed. The way it works is we start with an MRI. There is some segmentation going on to create a mesh from the MRI. At the same time, we are using rule-based fiber orientation because in the heart, and so the muscle fibers, they have a direction, and the signals travel along that direction quickly and slowly along other directions, which is, of course, a very important part for scientific simulations. And the result is the so-called virtual heart model. And I mean, it's a very limited form of a digital twin, right? But it's capable of predicting arrhythmia in a patient. And what medically, what we can do with this is we can, in a sense, we can virtually shock the heart, and see whether an arrhythmia arises. A procedure that until now was done clinically, as in the patient is being operated. The doctor is actually trying to induce arrhythmia. And if that happens, they restart the heart and figure out that this person needs treatment, either ICD device, right, cardiac defibrillator, or ablation, which means that you burn away some of the tissue and to in a sense, remove this possibility of arrhythmia. And the simulations can actually guide this ablation procedure as well. But the main thing is being able to do this in a simulation rather than in an actual patient's heart is a huge improvement. And a landmark study has actually shown that this is not only a lot less invasive, but also actually better, because you can test a lot more things here. And you can just keep more time. You spend a lot of time, can spend a lot of time running a lot of different simulations, something which you cannot do on an open heart. And okay, so what are we computing? Right, so this is the Lynx simulator, and which started about 10 years ago. This is talking about the fully explicit version. Right? And as Kengo already said, right? So we have a tetrahedral mesh of the heart, right? And we have a combination of ODE and PDE steps. We see PDE steps being the more, let's say, challenging one, because with respect to high performance computing. But the nice thing is, so essentially we perform a large number of identical time steps. Right? So these are the equations. That's has also already been shown, but I guess we are not going too much into detail. The main thing is that, right, so there is a there is a PDE part, the transmission of the signal, and the reaction, which is based on a very complicated, or modeling the very complicated opening and closing of gates in the cell membranes. And so, I mean, there's not only just a sort of a spreading of the signal, right, but each of the cells has its own reactions. And there is actually a large number of models for simulating that. And I think there are about 30 or 40 of these models of varying complexity. Right? So these are of medium complexity. It takes about 1,500 flops to compute one time step for one cell. And yes, we can split the operator, right? So essentially we have these two concerns. We have the PDE part and the ODE part. And of course, as Kengo said, ODE is embarrassingly parallel, right? We just need a lot of compute power to do that. There are obviously some optimizations going on there, but this is not very interesting with respect to parallel computing, right? The main thing is that we can do that we optimize the PDE part, right? And I mean, essentially here, the normal thing is we just iterate PDE and ODE parts, but the difference is, so the PDE part has a time step which shrinks with a higher resolution, right? So if we use a finer and finer mesh, we have to shrink our time step, while the ODE part has actually a fixed time step. So this means if we are going to larger and larger meshes, we may want to actually perform multiple PDE steps for one ODE step, because otherwise we are just computing too many more ODE steps than we would need. So this is why the PDE step is actually more important, right? Because in the extreme case, we could compute 100 PDE steps for one ODE step. And so essentially we have this computation, right? We are based on a sparse, essentially everything that is important about the PDE is in the sparse matrix that represents this mesh, right? And then essentially every tetrahedron has four neighbors, and each of those has 3 further neighbors, which gives us the cell plus 16 of its neighbors, right? And since it's a finite volume computation, that's the size of it, which makes the computation manageable, right? And essentially, how can we get this computation to extreme scale? That's the main question, right? Or can we compute this fast? So the tetrahedron has its neighbors, right? And here we'll see how many neighbors we actually have, right? Because I mean, one thing is if we are on the boundary, right? We don't, a cell does not have all the 16 neighbors, or some of the neighbors, right? So the second degree neighbors could be the same again. So in that case, it's also, right? So that's why most of them actually have 15 rather than 16 neighbors. But the main thing is, this is what we call an ELL or ELL-PACS matrix, right? We store the matrix by simply making essentially space for up to, this is basically an n by 16 matrix, right? And if there are, I mean, somebody doesn't have all the neighbors, right? Then we just pad this. And because it's so rare that cells have few neighbors, this is very efficient. Right? We use a little bit of padding, do a little bit of unnecessary work, but in exchange, we just have this, we don't have the complexities that you usually have with sparse matrices. We know that every row has exactly 16, and addressing each of these positions and so on, it's much faster than a typical CSR style matrix, especially on GPUs. Right? And the nice thing is also we can use 1D partitioning, and because the work is exactly the same for each cell. Right? We always perform, right? I mean, we always read 16 elements here for each cell. And now the main thing to get the performance is the ordering. Right? So, I mean, everybody, you have to access the vector elements based on the structure of the sparse matrix. And depending on how it is ordered, you either access them in a very, let's say unpredictable order, which means that your elements will most likely not be cached, right? Or you can try to reorder the matrix in such a way that all your accesses are very close together, that you keep hitting the same positions in cache. And of course, this is on CPUs, it's good. On with larger meshes and modern CPUs, it's better and gets better and better. And on GPUs, it's extremely important. So we get something like a 10x speed up by performing this reordering correctly, as opposed to essentially having the non-zeros in the ordering that we would get by just creating the matrix from the mesh, right? Because they are not on any kind of ordering, right? And then, so this is a procedure. It's not overly expensive to do that. We use actually a partitioner, a graph partitioner for doing that. It costs some time, but since we are performing so many time steps, we can amortize everything. And so we spend some time in the beginning. This costs something like 1,000 steps or so, but we perform 100,000 steps later with a 10x speed up. So this definitely pays off. And typically the things that we needed to get this fast, right? So since we have 16 non-zeros, we can do a full loop unrolling. Right? And in the case of GPUs, we perform block transposition. So we look at essentially we look at rows locally at rows instead of columns. An alternative would be to look at 2 rows at the same time. But the important thing is we have 16 elements, and the GPU has a warp size of 32. So you cannot just use one row of the GPU for each warp, right? Then you would get only exactly half the performance. So what we're doing is we are splitting off the diagonal, because the diagonal doesn't really need, every element has an entry on the diagonal in any case. The diagonal doesn't need any any index, right? Because we always know where the diagonal, right? So my diagonal index is exactly at the index of my position. So this kind of saves the indices, and it means that for the rest we are dealing with 16 elements instead of 17, which makes everything a lot faster to compute. And because 17 would mean that we cannot fit 2 of those in a warp, and that basically means we would lose half the performance. So this is a very involved or very low-level technique, but it's very important to get the full performance. Right? And I mean, this works quite nicely. So we have done a lot of performance prediction, like looking at how many bytes are actually being moved, right? So it's all memory-bound computation. And I mean, typically we are not very far below the stream numbers, right? So maybe if stream gives you 80% of the nominal memory bandwidth, then we are typically at 70 or so. Sometimes, in some cases, especially Volta GPUs, it's even higher. And so what we're doing is, right, I mean, okay, so we are partitioning this, right? And essentially, we use 1D partitioning, as I mentioned, right? Because we already have a good load balancing. And that basically means just all the off diagonal, I mean, so essentially we get on the diagonal, we get this blocks, right? Everything that is in the block doesn't need communication. If we minimize the elements which are not in the blocks, we minimize our communication, right? And of course, this is partitioning, right? So this cannot be computed exactly, it's NP hard, but we can use strong partitioner software to get this as good as possible. And so at the first level, right, so we are splitting for the nodes, right? We are making 1 part per node. Right? We are using partitioners such as Carhep, Pato, or Metis. And later what we're using also, we're using second layer of partitioning. So inside the node, we perform another level of partitioning. So that means that this means that we really prioritize the node-to-node connection, right? So we make those as good as possible. And then inside the node, you also partition, but this is not as important, right? Because inside the node, your communication is much faster. So we have used this back then, right? Back then, initially, this was used to just split work between multiple GPUs on a node or CPU and GPU on a node. And of course, we do renumbering for full scalability, right? Meaning that we only use as much memory as we need, right? So we do not use excess memory, right? So we don't keep, in a sense, empty parts of vectors. And another technique, which I will talk about in the next slide, is we reshuffle the things to get contiguous separators. And so this is one of these. So early on, we basically, I mean, this is what it looks like, right? So this is, for example, the heart looked at, or the ventricle looked at from above. And the colors are essentially the parts that you're getting from the partitioner. You can see that they're contiguous, meaning you only have communication on the edges, right? So the communication is relatively low because you get large continuous parts where you have no communication between the nodes. And so this was essentially looking at different communication metrics, something like the maximum volume of the node, and so how much the maximum node or average node has to communicate. Right? And of course, although the total communication volume is of course going up if you make more parts, right? So you make more cuts, so it has to go up. The volume per node is going down, right? Meaning that this remains scalable, right? And back then, so we projected performance. So this is a little bit, this is an old, based on an old machine, right? But I mean, the possible performance is going up unless you're, I mean, as long as your nodes are not too fast, right? If you have a lot of GPUs on a node, then you can run into problems because your communication on the node is not fast enough for the computation you can do on the GPUs. So for example, Lumi or so is a problematic machine for this because it has so much power on each node. And this is a little bit about the communication optimization, right? So we take the separator as in all the values that we need to communicate somewhere else, we pair them together and compute this first, right? And while the rest is being computed, we perform communication. And these are contiguous pieces, right? So you can directly use MPI calls. I mean, we later used neighborhood auto-OV, right? Which is this irregular communicator, but essentially it doesn't really do much else than just using MPI sends and receives, right? So it's not really a there's not a lot to do here with collectives or optimization of collectives, because it's really more like point-to-point connections. But the important thing here is, so this is irregular, right? So if you just have a list of elements that you need to grab these elements from memory, pack them into one array, and because I mean MPI means that you send arrays. But if you do this reordering first, you can actually, most of the data is just it's just exactly like this in memory, right? So this is a vector of the elements that need to be moved, right? This is how it's computed here. They're all one after the other in memory. And then we can just grab this and send it via MPI, and it lands in exactly the same order on the other node, right? This is, it sounds like a small change, but this packing is actually, it's surprisingly expensive. Right? Because I mean, you're just grabbing a whole cache line and then to get one element. And so avoiding that as much as possible was a substantial performance increase. And that definitely makes the communication, the entire thing, more scalable. Right? And then there is a small element, a number of elements, which have to be sent to more than one node. Right? So they're like on the corner of the of a subdomain. So for these, we still have to do the packing, but it's only like 5% of the total. So we get rid of 95% of the packing. And yeah, now we have a few, right? So this is essentially the machines that were presented. So we did older runs, right? But the newer runs are all on the local machines here. So this is the older Oakforest-PACS KNL machine. You can actually see so total time and ODE time, right? So it's basically, it follows very much with the ODE time. The PDE is quite fast because KNL is a high bandwidth memory machine. And the PDE, since we optimized it a lot, I mean, it's basically just running at the memory bandwidth. So, right, I mean, no matter what you do, so this is quite fast, and still, I mean, the speed ups basically come from computing the ODEs faster, and you can see this is 36x for, sorry, 63 for 64 nodes, right? So it's basically just linear because, I mean, it's embarrassingly parallel, right? And this is, there is some rounding in this. This essentially scales linearly with the number of nodes. So the PDE in this case scaled with 44. I mean, there was some, I mean, the communication on this thing might not have been optimal. And of course, the MPI doesn't scale that well, right? So the, I mean, there are some, I mean, the MPI takes a while. And that's got a total of 34. And here, this is OpenCX, right? So this is a Xeon-based system. And I believe this was Cascade Lake. And so you can see here, it's a little bit different. So here, actually, the PDE part is a lot more expensive in comparison because this is DRAM, not high bandwidth memory. DDR, I believe this is DDR4. And here, interestingly, the PDE is scaling super linearly. And the reason for that is once we get more nodes, and I mean, when we get more nodes, we have more cache, right? And a larger part of the entire element is being cached. And that means we actually get fast. I mean, we don't get, we get faster by more than a linear amount, right? And this is mostly because here the memory is slow and adding a lot of cache really helps. Right? And here, well, in this case, I mean, we start with a smaller number of nodes, right? So here, the MPI is actually scaling a little bit better, right? But that's mostly because we are on different, right? We started at a different point here. And so this is the last one, right? So this is Wisteria, kind of the. Then here we have a similar thing, but then again, this is high bandwidth memory again, right? So this means also, I mean, you can see here the PDE part is already relatively fast. So it doesn't really, I mean, it doesn't really change that much anymore. Right? So, I mean, of course, it gets, I mean, it has more cache and so on, but it's not getting that much faster. We actually spent some work, or my colleagues or postdocs at Simula spent some work on actually investigating sparse matrix vector on the Fujitsu processors a little bit more. There are interesting things you can do by introducing sector cache, but this was not being used here. And so it's possible that you could get the PDE even faster on this machine. But I mean, in all of these cases here, essentially, I mean, of course, the limiting factor is of course the communication, right? Because MPI is, I mean, it scales better than the other machines, right? It's a nicer network, but of course, this is not a very large instance. So, I mean, essentially, so the scaling limits are reached when you're, I mean, especially when the ODE part becomes so fast that it's sort of that that the communication becomes a limiting factor. Right? And at that point, I mean, you will get a little bit of speedups, but ultimately it will not. I mean, it will not really get faster anymore. And so there are limits. But then again, these are 2,000 nodes, right? Meaning that's 100,000 cores. That's already quite fast, right? That's almost a third of the machine. So if we had a little bit larger instance here, right, we could probably show scaling for. I mean, we have actually larger instances by now. They were just not made when this was tested. So technically, this would scale to the entire machine. And yeah, so this is a little bit historic, right? So as I said, so this is actually just about the explicit version of the Linux code, right? So I started this in 2013-14, right? So the original version had, on the original version, we were trying to use CPUs and GPUs at the same time, but that's not really very beneficial anymore because, I mean, modern GPU machines have so many GPUs and so much GPU power that the synchronization is too expensive. And the possibility of having the GPUs idle, and just having some GPUs idle is so bad compared to the benefit you can get from the small CPU part. It's just not worth it, right? So this is a computation which runs very well on CPUs or high bandwidth memory, GPUs or high bandwidth memory CPUs. And so we experimented with KNC back then, but it was quite clear that KNC could not do that at all. And so this was a failure. And 2016, we added a fully scalable matrix generator. And so essentially this takes the mesh. The original version was taking the mesh sequentially, right? And then creating the matrix from it and then distributing that. Now we can create the matrix fully distributed. It's a relatively complicated code, but that means that, I mean, if you have for very large meshes, right, the entire mesh generation, the entire matrix generation from the mesh can be done fully scalable, but we still have to create a large mesh. And so we do not have our own mesh generator in there. And so this was using something like TEDGen or more recently Gmesh and so on. And then we tested a lot of different communication strategies. I have not mentioned that here, but it is not so clear here under which, so it's not so easy to get the overlap running here. So the normal case was that we had one communication CPU and then which was, one communication core, right, which was performing the communication while all the other cores were computing. And this is, then again, this is not always clear how beneficial that is because it's very difficult to get this memory bound, bandwidth bound, right? And you can throttle you can throttle the core that is communicating by doing too much computation on the other cores. And initially, we were investigating that on old CPUs, and then some colleagues of mine in Bordeaux at INRIA, they continued this line of experiments, and they actually found that it's even worse there. So modern CPUs are even more susceptible to that. So it's getting overlap really going is a very challenging thing to do. Yeah, and then, so 2018, one of our students who's involved in this project created a GPU, multi-GPU version with sort of, with really speeding up the ODEs, right? And he managed to get approximately 80% of the machine performance on Volta. Interestingly, both PDE part and ODE part. And then, so this is basically based on the version of James Trotter, who's postdoc at Simula now. So this is, the results are based on that. And yes, Kengo already mentioned the GPU version. And what I'm going to talk now is the IPU version. So the IPU is a new device. It's an AI accelerator. So this was specifically made, or at least made with running neural networks in mind. And it's a big departure. So this is after GPUs. This is maybe the first real interesting or major change in hardware technology for the last 10 years. So the important thing here is that it doesn't really have DRAM memory. It has essentially, cache as in SRAM and uses that as memory, which means you just need a lot of these chips to run large applications. But, well, the benefit is it has insane memory bandwidth. If all the data is exactly where you need it, is really, really fast, and it has lots of cores. So you can do a lot of things with it if you manage to get your computation in such a way that it's really, that it's perfectly laid out for that. The only interesting thing is, so it has, since it is optimized for deep learning, it has a lot of flops in matrix units, right? But not so much general flops, meaning you can only use the high flop numbers if you're doing dense matrix multiplies, which we're not really doing in scientific computing very much. And yeah, this is a little bit what it looks like, right? So there is a big exchange, so that connects all these cores individually, and each core is called, it's paired together. I mean, each core has 6 threads which just rotate in fashion, right? So they don't have normal multi-threading. It's more like, it's called a barrel processor, right? So they just iterate one after the other. And interestingly, the instructions also take 6 cycles, which means that, okay, so a thread gets scheduled, right? And then 6 cycles pass, and then it's back with the result. So the individual thread doesn't really see any latency. And so you do not need to optimize for latency or anything there. It just runs as long as you can occupy 6 threads on 472 cores. So if you can split your work in that way, and I mean, all of this works very nicely and very smoothly. And each core is paired with 624 kilobytes of memory, which is very small. And our view on that was essentially, I mean, we know how to program distributed memory systems. And let's program this essentially just like a small distributed memory system. And the way it works here is essentially there is an interleave between, I mean, it's kind of based on the data flow model, right? So you have data, which, I mean, it's called tensors it's modeled after TensorFlow, right? In between, computation happens, right? And then there is a state, which means that essentially you cannot really overlap anything. Right? So this is what we call a BSP, bulk synchronous parallel model in parallel computing. And so you have computations, they could take different amount of time, but to communicate with some other tiles, you have to basically wait for the communication round. So everything has to be done before you can communicate, meaning the tiles or the cores always wait for the slowest core, which means that you have a massive load balancing problem. So you have to really take care or really deal with the load imbalance in your problem. Otherwise, this will not work. Right? And then there is a problem that the compiler of this is a little bit tricky. It requires predefined communication. So getting this to work on irregular applications is a bit tricky. But we managed to get this to work. Right? And we have to simplify this thing here, because actually keeping records of which elements are needed where, right, and which parts are needed where, and so on, this actually takes memory. Right, and you have 1,000 neighbors, or I mean, you have 1,470, you could say, ranks. Right, thinking about MPI in this machine, right, and storing the sizes of all of this and what goes where and so on is actually, it's a little bit inefficient. So we had to simplify this a little bit, right? So you don't actually communicate the minimum, the exact minimum, and you communicate essentially more or less overlapping parts of this part here. So essentially all the stuff gets communicated. This is not a big problem inside the device because you have 8 terabyte of per second communication. It's so fast that it doesn't really matter. Right? It only matters, and yeah, this is basically, that's what communication looks like, right? So you can maybe, I mean, you have the smaller, the near ones, which is, these are the fastest communications. Communicating across the device is a little bit slower, but it doesn't really matter too much, right? Because the programs you can run on this one machine, they're so small that I mean, it's just fast enough for us. And the problems actually appear when we go to multiple devices. Right? And I mean, essentially what we're doing here, right? Okay, so we have this individual parts or the individual, and I mean, it's just like in the MPI case, right? So we cut the problem apart into, in this case, 1,472 parts, right? And assign them to the individual tiles. And essentially we use the same strategy that we used for the distributed memory machines. But of course, we can only run smaller instances here. So in this case, we run the largest instance that fits on one IPU has 3 million cells rather than the 50 million that we were working. And so a student of ours implemented this on this IPU machine and ran this against the A100. And this was one of the results. So the GPU wins, but the interesting thing is the GPU wins because it's so much faster on the ODE. And as I said, so this device doesn't have a lot of flops that you can use for the ODE computation. And the ODE computation is not small. So when using this specific ionic model, and there is a bit of a problem here because I mean, you can actually see that this doesn't entirely sort of, but I mean, in any case, so the PDE computation is actually faster. But with this ionic model, so maybe with a small ionic model, the IPU would win. But it doesn't win because, not because, I mean, in a sense, it's very good at doing the difficult, the PDE part, but it's weak at doing the easy, the ODE part. And we try to run this on multiple IPUs because we want to run larger instances, right? And multiple IPUs, when you essentially, you have connections between the devices, which are PCIe type connections. So each of these links is 64 gigabyte per second. You have links between pairs, and then they're kind of ordered in a ladder in a 1D fashion. So it's, yeah, I mean, communication, once you get larger sets of these machines, communication becomes more and more difficult. Right? But I mean, you can communicate across these. And we spent some time of actually finding optimum assignment, right? So finding which piece exactly goes where. We computed an optimum assignment of that, and that helped a little bit. And there are some comparison results. So 4 is a smaller mesh, right? Which is, and 5 is a slightly larger mesh, which doesn't fit on one IPU, right? You need at least 2 IPUs for this. And so what we have gotten is approximately a 1:2 ratio. If we did use this multi-stepping, right? If we perform multiple PDE steps for one ODE step, then the ratio would be much better, right? Because I mean, the actual, let's say, I mean, in principle, the PDE is much faster on the IPU, but the total is not. So in a sense, we are not entirely convinced under which circumstances the IPU can work. So I mean, if you have things which are much more memory heavy and and have almost no compute, IPUs tend to be better. We have also tried to experiment with breadth first searches. It's not included here, right? So then the picture is a bit different, right? But yeah, and I mean, here we have the case that adding extra GPUs doesn't help because GPUs need a lot more parallelism. And I mean, this one here is actually quite nice in cutting this apart into very small pieces, right? So if you have only a few elements per core, it still works, right? And the latency is very low. And this is a little bit of the overview, right? So the exchange, as in the communication, of course, goes up once you go to multiple pieces, right? But I mean, the main problem is when you can actually see here, right? I mean, the PDE part shrinks and the ODE part shrinks. But I mean, it's dominated by the ODE computation. And since there are some limitations with that, we are looking at a different device right now. That's a so-called serial bus wafer scale engine, which is potentially more interesting than the IPU. And so far, it's more radical. It essentially takes the entire wafer that is being produced, and instead of usually like cutting it apart to produce something like 60 or so chips, this entire wafer becomes one computation device. It's essentially one, it works as one processor with approximately 850,000 of these tiny cores. Okay? So here, the cores are even smaller. They're connected in 2D, right? So you don't have this kind of auto-OR capabilities that you have on the IPU. You are in a 2D grid, but you can compute your, your computation, your communication and so on, you can actually program that yourself. Right? And in total, right, aggregate, this is very fast, but you may have to sort of spend a lot of time optimizing that, or a lot of thought on how to optimize this if this is irregular and you have to communicate between different parts of this 2D device. So essentially that's what we have started working on that. And it's quite clear. So there is it's more complex than programming the IPUs, but of course there's a potential for more reward because you have so much power in one single device. And so you have approximately 64 or so IPUs or GPUs in one chip. And yeah, this is pretty much the lessons here, right? Essentially here, IPU works pretty good. And this MPI-inspired strategy, right, of seeing this as a distributed memory machine worked quite well, right? But essentially, the main thing here is that the way this device is implemented, there is a slow ODE, but then again, there is nothing in principle that would prevent Graphcore from making a device that instead of these matrix units had 64-bit. And you could design, you could easily build the same device, but optimize it for scientific computing. Of course, the question is whether there is a market for it, right? Whether that's realistic, but just from the design, this would be no problem, right? So this being slow on the ODE is not really a fundamental drawback of the entire idea, right? That's more like a problem with this specific chip. And on the on the Cerebras, it has a lot of potential. However, and we had 600 kilobytes per core here. Here we have 48 kilobytes, so it's even smaller. Wow. So the problem is, we are pretty sure that this MPI-inspired strategy, and just seeing it as a tiny distributed memory machine, will not work. You need very different things. So when we are looking at doing things here, and that basically means that you have to specialize some cores. Right? So it's not like MPI-like, where every core kind of does the same, or where every rank does the same thing on different part of the data. And we were actually experimenting with putting some special functions, like for example, aggregating data and then reducing the data that comes through, and just putting special functions or putting some chips aside to do individual functions. Right? And this is very much, that's radically departing from traditional supercomputing patterns. So that may need a lot of thought about new algorithms for this. Yeah. And yeah, so this is the team, right? So Shinkai was already mentioned, right? So he's the leader of the project, and the other three. So Luke is the one who programmed the IPU. James is the one who programmed the CPU version, right? Including the implicit method that Kengo was discussing now. And Christian was, he's also working on that. And he's especially was the one who got the fast ODE on the GPU. Yes, and well, as you can see, I enjoyed my stay in Japan very much. So yeah. So the joke is this is me working on Fugaku as I'm sitting with a paper on my foot. Okay. Oh, thank you, and I'll be happy to take any questions.
So it's nice to the next session. So next presentation also in the video recording. So if you have a question, please ask for the Yohei Miki, and the email address may be right here. So the title is Performance Evaluation of NVIDIA Code on NVIDIA H100 PCIe and AMD MY210. It's like started.
I'm Yohei Miki from the University of Tokyo. Today I will present the performance evaluation of gravitational NVIDIA simulation on NVIDIA H100 GPUs and also on AMD MI210 GPU. Unfortunately, I cannot attend today's ASE seminar even online. So if you have any question, please email to this address. Is a dominant accelerator device on recent supercomputers. And the GPU is a parallel computer equipped with many cores. In recent GPUs, there are around 10,000 cores. And the majority of current GPU supercomputers are equipped with NVIDIA GPUs, but recently there are also AMD GPU accelerated supercomputers. For example, Frontier, the current #1 machine on the top 500 list, is accelerated by AMD MI250X GPU. And also, Aurora, Intel GPU accelerated system, already announced. So recently there are competition among GPU vendors, and this competition drives performance improvement for GPUs. And in case of NVIDIA GPUs, so there from the Pascal to Ampere generations, there are around 1.4 times acceleration in each generation. But in case of the Hopper generation, there are 3 times acceleration. And also, announcement of GPU, new GPU sometimes includes the release of additional features, like providing new functions. And so we need to find out how to optimize for each GPU by each vendor. And this figure shows a performance comparison between AMD MI100 GPU and NVIDIA A100 GPU. And the performance is shown as a function of the particle number. And the red curve shows the performance for AMD GPU, and black curves are for NVIDIA GPUs. And if we focus on this, the highest case, there are almost the same performance on AMD GPU and NVIDIA GPU. So we have developed NVIDIA code and also optimized for the recent or latest GPUs. And that is NVIDIA H100 GPU and also AMD MI210 GPU. Okay. In case of NVIDIA GPUs, there are performance improvement from A100 GPUs to H100 PCIe version is around 2.6 times acceleration. And okay, the main reason of this significant improvement is a number of increased number of floating point cores per streaming multiprocessor, that is doubled. On the other hand, the number of integer cores or superfunction units per streaming multiprocessors are not doubled. And also, H100 SXM version have more streaming multiprocessors and also higher frequency and higher TDP. There are many new features in H100 or CUDA 12, but here are examples of the new features. But in case of direct n-body simulations, we thread block cluster or dynamic programming are not used. Here is a brief introduction of n-body simulation. In n-body simulation, we calculate time evolution of gravitational many-body system like this by solving Newton's equation of motion. In case of the direct n-body simulation, we calculate gravitational acceleration one by one like this. And in many cases, we call I particles as particle fields gravity, and also J particle as particle causes gravity. So in this diagram, this particle is I particle, and all other particles are called as J particles. And I and J is coming from this equation. And this is a summary of implementation and optimization for NVIDIA GPUs. For reciprocal square root, we use R square root of F function because this is the fastest on NVIDIA GPUs. And in NVIDIA code, there are many parameters. For example, number of threads per thread block, or number of loop unrolling counts. To find the best configuration, we perform the parameter survey using 4 million particles. And here is the result of the parameter study. In the main performance evaluation, we measured the execution time of gravity calculation, and also measured GPU temperature and power and clock frequency. And if possible, we changed and measured the charge fan speed by using IPMI. And in this performance evaluation, we used 4 million or 4 million, 8 million, 16 million, and 32 million particles. And in each case, we performed 10 measurements. And to measure GPU temperature precisely, so we set 10 minutes cooling time before job execution. And here is a summary of the performance evaluation environment. And this is a result for NVIDIA GPUs. And x-axis is the number of particles, and y-axis is performance. And maximum of 10 measurements are plotted in this figure. And in case of 800 GPUs, the performance is flat as a function of n. And from here, 800 GPU is twice faster in this case. And for 800 GPUs, there are four lines. And the first line is this black dotted curve is results on Pegasus supercomputers. That is 800 PCI Express version. And the other three curves are the result of 800 PCI Express version and also on our servers, and changing the fan speed of the server. And the red one is the slowest fan speed, or in other words, highest temperature case. And the blue one is the fastest fan speed and lowest GPU temperature case. Due to summer throttling, the clock frequency of GPU is decreased. So therefore, in case of this case, performance drops significantly. Also, we observed twice acceleration, but the theoretical peak performance ratio is 2.6, so there is a big gap. And the main reason is reciprocal square root function. And in case of NVIDIA GPU, reciprocal square root is calculated by superfunction unit. But the number of superfunction units per streaming multiprocessor is not increased in each 100K GPUs. So that is the main reason of this performance gap. Okay, and so we monitor GPU temperature and clock frequency and power during n-body simulations. To do that, we write code like this. We utilized unused cores for n-body simulation to monitor GPU status and observe such metrics in 0.1 second intervals. And yeah, okay. And the result of the monitored status is like that. And right-hand panels are results for 800 GPU. In this environment, Aquarius is our supercomputers and water-cooled system. And here is the time evolution of okay, this one is a temperature evolution as a function of time, and temperature is around 40 degrees, so very cooled system. Also, this is a power consumption, and power consumption is around 250 watts, and this value is sufficiently lower than this TDP. So therefore, the clock frequency is always fixed to boost clock. Therefore, the performance on Aquarius system is very stable. On the other hand, in case of H100 GPU case, first on the Pegasus supercomputer case, the temperatures go up to around 80 degrees Celsius, and power consumption is around summer designed powers, and therefore the clock frequency is relatively smaller than this boost clock. Also, in case of our GPU server, if we minimize the fan speed, so this red curve case, GPU temperature goes up to 90 degrees Celsius, then the clock frequency drops down to 1.3 gigahertz, and this is the main reason for the performance degrade. Also, in this case, power consumption is also drops to around 240 watts. So, okay, that is a result for NVIDIA GPUs. And let's move to the AMD GPU case. So first, the floating, in case for the floating point performance, and vector FP32 operation is like a normal operation in single precision, and the performance of the vector FP32 is of the MI210 is little bit smaller than all the MI100 GPUs, but in this generation, in this CDNA2 generation, there are new instruction sets named packed FP32 instructions. This instruction set doubles if fused multiply add and addition and also multiplication performance. So using this instruction set is the required to obtain the full performance of CDNA2 GPUs. And so the in optimization for CDNA2, the utilization of this packed FP32 instructions is nearly mandatory. And in case of the n-body code, we can use this packed FP32 instructions except for the reciprocal square root. And the expected acceleration is 5/3 times. And in this slide, I show you example to use this packed FP32 instructions. So, and also this is an implementation in HIP C++. And to use this instruction sets, we use float2 type variables. And in the interaction part, we describe the code as this. And there are special treatment for reciprocal square root like this. So this is a basic implementation for AMD GPUs. And in case of the AMD GPUs, we use this function to calculate reciprocal square root. And like NVIDIA GPU case, we performed parameter survey to find the best configuration. And in this case, how to use packed FP32 is an additional option for AMD GPUs. And the measurable performance of AMD GPU is like that. X-axis is the number of particles, and Y-axis is the number of interactions per second. And maximum value in 10 measurements are plotted in this figure. And the lowest curves is this for the results for MI100 GPUs. And when we use MI210 GPU without packed FP32 instructions, we observed 1.07 acceleration from MI100 GPUs. But the theoretical peak performance is slower for MI210 GPUs. So we surprised this result. Also, when we use packed FP32 instruction, then we observed 1.3 times acceleration. But unfortunately, expected speed up was 5/3. And also in this platform, we change chassis fan speed, but there are very weak dependence on the fan speed on AMD GPU case. Okay, and this figure shows the GPU status as a function of time, and results for AMD MI100 GPUs and MI210 GPU with packed FP32 instructions are very similar, and power consumption reaches to the TBP, and then the observed clock frequency is decreased from the boost clock, like this and this. And in case of the MI210 GPUs with vector FP32 instructions, there is a small gap between the observed power and TBP. Then the observed clock frequency is fixed to boost clock. Therefore, in this case, there are enough power supply for n-body simulation. But in case of these panels and these panels, there are not enough power supplies. Therefore, the clock frequency is decreased and also performance is decreased. And then this figure is a comparison of NVIDIA GPUs and AMD GPUs. And the results for NVIDIA A100 and AMD MI100 is almost the same, almost the same performance. From here, so NVIDIA H100 GPUs shows a significant performance improvement. And in case of the MI200 GPUs, the utilization of packed FP32 instruction is most significant effect. And here I show you the energy efficiency of the NVIDIA GPUs. And x-axis is the number of n-body particles, and the y-axis is the number of interactions per watt. And in this measurement, we measured only for GPU power, so we did not measure the power consumption by CPU or cooling or something like that. And so in this figure, we observed 1.5 times improvement for energy efficiency. And in case of this red curve, so this is a slowest fan speed case and highest GPU temperature case. In this case, so the clock frequency of the GPU drops significantly, and therefore the power consumption per time are also decreased. It results in this improvement in energy efficiency. And here is a similar result for AMD GPU. And this curves results for AMD MI100 GPUs. From here, there are 1.2 times improvement for MI210 GPU. Also, if we use packed FP32 instructions, we have additional 1.2 times improvement for energy efficiency. And here is a comparison of NVIDIA and AMD GPU case. Basically, NVIDIA GPUs shows a better energy efficiency, but basically this is because the process rule of each GPUs, so the this one's and this one's for 7 nanometer TSMC case, and this one is 6 nanometer, and this one is 4 nanometer case. So this is therefore the H100 GPU is the most power efficient GPUs in this comparison. And here I show you some performance projection for the flagship GPUs. H100 SXM is 1.3 times faster than PCIe Express version, and also there are sufficient power supply, so there are doubled TDP, so we can expect H100 GPUs runs always in boost clock. Then the expected performance is like this. And if we assume 26 flops per interaction, then this value is converted to 47 teraflops in single precision. This is almost 50 times than M2090 GPUs and in the film generation. And this is almost similar to almost the same to the peak performance ratio between both GPUs. And in case of AMD MI250X, so MI250 is like 2 MI210 GPUs. So there are double compute units and the same clock frequency, but the total board power is only 1.9 times. And also MI250X has additional compute units with same TBP with MI250. So we believe there are more serious shortage of power supply on these GPUs. But if we assume the frequency decrease is the same with MI210 case, then the expected performance is this value, and this value is 10% higher than H100 SXM, but further frequency decrease may occur. Okay, here is a summary of today's presentation. We have developed NVIDIA code and optimized for NVIDIA and AMD the latest GPUs. And H100 is PCI Express version is twice faster than 100 GPU, and AMD MI210 is 1.4 times faster than MI100 GPUs. And both GPUs show around 1.5 times better performance per watt than predecessors. Okay, that's all. Thank you for your attention.
Thank you, Miki-san. This is our video presentation. So if you have some questions, please free to ask Miki-sensei. So let's start the presentation. The next presentation is Yuan-san. Its title is Accelerating Lattice Boltzmann Method Using a C++ Standard Parallelization on GPU. So please start the presentation.
Hello everyone. My name is Ziheng Yuan from Graduate School of Engineering at the University of Tokyo. Today I will talk about accelerating the lattice Boltzmann method with GPU and C++ standard parallelization. So first I will briefly introduce the research topic. The lattice Boltzmann method, also referred to as LBM, is one of the analysis methods for fluid simulation. The LBM simulates fluid behavior by modeling the distribution of particle velocities on discrete lattice grid. The LBM algorithm is easily formulated in parallel and can efficiently utilize GPUs. When combined with the inverse boundary method, LBM can handle flows with complex boundary conditions. LBM often involves the allocation of multiple variables on each grid node, which can lead to increased memory access during computations. If you aim to execute LVM code on GPU, utilizing C++ standard language parallel algorithm is a viable option. C++ standard parallel algorithms allows tasks execute concurrently, enabling parallel processing. There are several characteristics of the C++ parallel algorithms. The main purpose of this research is to accelerating the LVM code using the C++ standard language parallel algorithm and verify its performance in single GPU and multi-GPU case. To achieve this goal, we need to parallelize the LVM code with the standard parallel algorithm and optimize its memory transfer performance. So first, I will briefly explain the lattice Boltzmann method. It is based on the discretized Boltzmann equation, where the fluid is regarded as a collection of small particles, and the fluid movement is simulated by the movement of these particles, as shown in the figure 1. In the LBM D2Q9 model, the fluid particles velocity is limited to the 9 possible directions. And the LBM process involves 2 main steps. The first step is the streaming step, which simulates the movement of particles in the current time step and involves copying data multiple times. The second step is a collision step, where the particle collision are simulated, involving more computation than the previous step. Figure 2 presents the results of the fluid passing through a cylinder, solved by the inverse boundary lattice Boltzmann method. In this experiment, we will solve this problem using the we will focus on solving this kind of problem. Okay, so in the first equation, the streaming model updates the distribution function to the next time step. The collision operator simulates the collision step. Many collision models are available for the LBM method. In this experiment, we choose a BJK collision model. We calculate the collision operator with the equilibrium distribution function. If the inverse boundary method is applied, we need to update the distribution function again. This will be introduced in next slide. After the distribution function gets updated, we could use the function to calculate the density and the velocity. In inverse boundary LBM, the distribution function is corrected by the body force. And one of the calculation methods of the body force is a multi-direct forcing method. The flow velocity as a boundary point arbitrarily taken in this way is calculated from the flow velocity of the grid point within the surrounding grid, and the body force of the boundary point. Body force of the grid points, the flow velocity of the grid points are calculated. Figure 1 shows the workflow of calculating the body force G, and in the previous studies have shown that repeating this loop for 5 times will satisfy the condition. So next we will talk about the C++ standard parallel algorithm. By adding the execution policy, algorithm will work in serial or parallel, and many commonly used functions include the SDD execution part or the SDD execution part unsequential. Supports this execution policy. Most of the algorithms from these 2 libraries support execution policy. In this experiment, we mainly use the SDD for each end to parallelize the for loop. The standard parallel algorithm supports a unified memory. As we all know, the CPU and the GPU memory space doesn't share the memory address. So program needs to copy data from CPU to GPU manually and vice versa. Unified memory could virtually share the memory address with the CPU and GPU. So a programmer could use a variables pointer directly without considering the memory transfer. Unified memory works well in the CPU to GPU communication. However, unified memory cannot handle GPU to GPU communication, and we will solve this problem later. Next topic is multi-GPU computing. In multi-GPU case, the entire computation domain is evenly divided. However, since the computing age, the age portion requires obtaining data stored on the neighboring GPUs. It is necessary to use MPI to communicate between the GPUs, and the communication consumes lots of time. In order to simplify the communication, a domain named hollow is added. Data from other GPUs are stored in the hollow, and there are several factors affecting communication speed. The first one is the CUDA-aware MPI, which is supported by the NVIDIA GPUs. The original GPU MPI only supports the CPU communication. So if we directly apply the MPI to the variables stored in the unified memory, the data must first be transferred from GPU to CPU and then communicated to the target GPUs. This would result an unbearable amount of the time consumption. And the CUDA-aware MPI allows to the GPU to GPU communication directly and reduce the time consumption. However, it is important to note that the CUDA-aware MPI does not currently support unified memory. So the second is the data layout. Since the global data needs to be accessed by multiple threads at the same time, the data layout will affect the access efficiency. Those topics will be introduced in the following slides. The first factor is the CUDA-aware MPI. To utilize the CUDA-aware MPI for the communication, pinned memory buffer are required. Although it might contradict with the policy of not applying other program languages. Nowadays, only the memory space allocated by the CUDA malloc or the source device vector could be used as a buffer. We first transfer the blue region data stored in the unified memory to the green pinned memory. After that, the data will be transferred by the CUDA-aware MPI. All of the data that needs to be transferred includes the equilibrium distribution function or the density or the velocity of the fluid will be stored into the buffer and send it with one MPI call. So the number of MPI call could be reduced. And after the transfer finished, the data will be fetched from the buffer and stored in the target unified memory space. In the immersive boundary method, information about the cylinder object in the fluid, include force and velocity, will be stored and computed on each GPU node. After the computation for each time step is completed, the algorithm requires collecting body force data from each GPU node. Therefore, the MPI or reduce function is necessary. To enhance the communication speed, it is possible to pre-store the body force data in the pinned memory buffer. As a result, the reduction option will also benefit from the CUDA-aware MPI. So the second factor is the data layout. There are two different types of the data layout. First is the array of structure. This structure stores all of the information of each RBM grid node in serial. Take the equilibrium function as an example. This structure will store each grid 0 to from 0 to 8 direction data together. It is easy to understand, but unable to access a memory core list. Another type is a structure of array. This structure stores the grid store the direction 0 of each grid together, and is efficient in memory access. Since every wrap of the GPU could fetch the target grid nodes information in serial, and so it's efficient in the memory access. We will compare the performance of each layout. So this is the experimental condition we use. The computer is a Victoria Oakforest high performance computing platform, and the number of GPU used is NVIDIA A100 times 8. The compiler we choose is NVIDIA HPC SDK, and the size of the computational domain is the 8,000 times 8,000. The data layout is a structural array, and an array of structure. We will evaluate these two values to analyze its performance. First is MLVPS, the mega lattice update per second. It is used to compare the performance of the code, and also the drag coefficient is the sum of the force taken by the cylinder in the float. We will use this value to verify the correctness of the data. So first is a single GPU performance. We will take it as a benchmark to compare the performance. In this experiment, we have the code solves the same problem and written in two different forms. First is a CUDA version, which use CUDA and MPI to solve the problem, and it is the benchmark of the experiment. The other one is a code written by the C++ standard parallel algorithm and MPI. We can see that the performance of the C++ standard SDD part is close to the CUDA version, and also when we compare the drag coefficient, the error of the difference between the two code is less than 10 times -5. In this experiment, we did not apply the CUDA buffer to the C++ standard part, and we only we transfer the data stored in the unified memory directly, and compare the performance. From this figure, we can show that the MPI communication limits the performance of the C++ standard parallelism code, and the performance of the code get reduced when the number of GPU increases. And after that, we apply the CUDA buffer to the code. So the performance of the C++ code gets increased for 63%. And compared with the performance of the code, only applying CUDA buffer to the boundary exchanger. Apply buffer to both boundary exchanger and MPL reduce will increase the performance slightly more. We can see the difference from the figure. And CUDA buffer allows to exchange all variables in one MPI call, which reduces the communications cost. So this is the reason why the C++ standard part SDD part code performance is higher than the CUDA version. And finally, we compare the data layout, the effect of the data layout, and from this figure we can see that compared with the array of structure of array increase the memory access speed. So in conclusion, in this experiment we investigate the optimization method for LBM, and also we find that the performance of the SD part is better than the original CUDA method, and also applying the CUDA buffer could increase the communication performance. So that's all. Thank you for listening.
Thank you for listening, Ian-san. So, final talk is from Shinichi Mimoto. It's a kind of status of Oakforest-PACS. So this is maybe many predicted Toshi Hanawa sensei, but instead of him, I talk about some talk from using some Hana Sensei's slide. So here's the outline of my talk. So first, I'd like to introduce the more JHPC and the Oakforest-PACS. But maybe from the first talk, Nakajima Sensei will talk about that. So I maybe some skip over this thing, and then go to some how do they design for next generation of the Oakforest-PACS system, and then go to our efforts supporting of the GPU, and then go to some of the latest research for the project on JFCM, which is GPU direct storage and plugin for GPU. And finally, I took some of our test bed for the Oakforest-PACS. So we are now developing and including some small type of with market systems. I took some brief overview of the system. So let's go to the first topic. So maybe from the Nakajima Sensei will talk about the JHPC, the Joint Center for Advanced HPC. So it's established 2013. It's a joint of the University of Tsukuba and the University of Tokyo. So it does mean it's a budget of two supercomputing centers are combined. So that is because we are making more bigger machines from to combine the two budget. So this is some of the use case of some promotion in the computational science, design, procurement, operation with a large scale system. I mean the way of promotion to that. So that's the first machine, the Oakforest-PACS. It's called the OFP. It's the first system of JHPC. It's around 8,000 nodes Intel Xeon Phi. It's 90 rounding, and it's about 25 petaflops made by Fujitsu. And it's almost rank 9 at the November 2016 rank, and it's also the #1 in Japan. So it actually is a national flagship system. In fact, if you October 2019 to March 2091, after shutdown of the K computer and the coming up of the next generation of PCIe. But this system is retired on March 31st in the 2020s. It's at the time rank number 39 at the November 2021, 31st. So after that, so we are starting procurement of the OFP2, the successor of OFP, whose operation is start in April 2024, but it's coming late. So I talk some about how OFP used from the 2017 to the 2021. It actually in the first of the 2 years, it is half of the occupied by QC US because there are big ways than the Tsukuba University usually, and also increase the space and the science. And this kind of stuff is moved to the Oakforest effects. It is a Spark based and a commercial version of K computer. And after that, it's 2019. It's still the science is larger than QCD. It is a user from the K computer. We don't know, but and also it's important thing that increase the data science, simulation, and maybe a trial of simulation. So in the 19th later, and then in the 2020 and 2021, and it's a bioscience, informatics, COVID-19. And also using some simulation of Tokyo Olympic Games, and also 2021, yeah, QC portion is dominant again. It's last time the OFP, and many users for us space move to the virtual background. That is because okay. And also engineering is so big ratio because some of effects and reduction of OBX to the move to here. So I took some, it's not enough time to explain that. It's used by the real-time prediction of severe rainstorm by OP. It's a Japanese called guerrilla go. It's in Japanese. It's a severe rainstorm. At the time, there are some radar around that. Here, getting radar is some of the periods, maybe cloud. In that case, some cloud is spreading so faster and faster. So in that case, we have to predict such kind of a severe rainstorm. It's around within 30 minutes. So we actually some project. It is some majorly currently operating at the Fugaku, but because the starting Fugaku, some severe rainstorms users use Oakforest-PACS to developing some of their applications, and then also move to Fugaku and now operating. The other thing is HPC, an urgent call for fighting against COVID-19 in Japan. It is a financial year 2020. So it is provided by 8 supercomputing centers in the National University and on the ASE. And also maybe 6 of 14 accepted projects use our machine. That is one thing, the fragment molecular orbital collection on the main proteins in the COVID-19, and also some prediction counter measurement for various droplet inflection and the indoor environment. Such a thing. So you can use some of with propagating some video or TV. You can. This is very famous. But this kind of stuff is also developed by OP. So let's talk about the next machine. Before that, I'd like to talk about supercomputer in the University of Tokyo since 2000. In that case, some of at the first time it also use maybe a Pagero vector developed by Hitachi, then going to some of much core CPU. This is a power CPU and maybe in the AMD Opera base and mediated G cluster. Also, some of providing FX10, which are FX, that is a commercial version of K computer, and the G15 and maybe Cascade Lake, something like that. After that, some GPU accelerator coming in the operated by the Reed Bush, and some now we are operating with the BX01. And next target now in the OFP2. So how do you think of some next machine? It's some explanation of the research area. Maybe it's some statistics about 2021 in the University of Tokyo. So Reed Bush GPU cluster. It is a bioinformatics and some AI and material science. This is a green one is based on the GPU machine, and the blue one is some CPU-based machine. So OFP is usually CPU machine, and OBCX and ODC are GPU machine, and Aquarius is a GPU machine. So how do you think about that? So usually this time OBCX retired this month, the end of the month. So we are thinking about some Oakforest-PACS, but also some follow-up to the OBX user. That's our main requirement. So how do you start a generation system? So this is some event for the next generation machine. So November 2019, we agreed to continue design and operation of the second generation of the system at JHPC. So we can make a contract. And next February, February 21st, it defines the code name as Oakforest-PACS 2. And November next 2 year, November 2022, it start the procurement procedure and the request for information. And that at that time, so April 24th is the target operation start. Yeah. And also in OFP was the top machine in the top HPC second tier system. So actually some OFP could run 20,000 node job at any time and keep the supporting Japanese computer resource being computer decommission and the flag completion start. That's very, also it's a requirement. So that's kind of influence for philosophy of the OFP. Support for users of large-scale application continuous. That's a very important thing. So the new thing, the new usage, AI for HPS, HPC and science, and also collaboration application is very important. So how do you think that? So I took some development for new types of application. It's a highly developed simulation by integration of simulation and data and learning. X plus D space is very important and enable more tightly coupled corporate data, like some of data simulation plus simulation, and also simulation parameter estimation by machine learning and some calculation. That will be so far we call some AI for HPC and science, and almost we use advancing efforts on the visual plan or signal figures of the University of Cuba, and also visual, as you know, some visual business run consists both Odyssey simulation node and node acceleration data learning node, and other signals provide some extreme computing with much heterogeneous accelerator, and also Pegasus will provide big data and AI. That kind of stuff which essence is needs combined. So requirement for the carbon neutrality and power efficiency is very important. That is because of the introduction of GPU for most of computer resources, and still need some simulation of the CPU node. That will support the OBC. So let's get the previous benchmark for the office that I talked about. So that's the design. So it's estimated that over 3,000 users of the OFP in the around current system. So it also provides such kind of number of users. However, it is difficult to perfectly migrate users to use GPU cluster. So you are still considered as this visual business one, but finally gave up. It's some fall in 2019. So because there are some various kind of GPUs and various programming environment for GPU. For example, OpenFCC, OpenAP 5.0, or target offloading, or some previous talk, standard language support. Better for the OpenAP users for OP than the foreign thing. And there's another program language, CUDA, HIP, and SECU. And which market for the prototype OFP2 anticipate for porting application on the GPU count installing. And some original plan was node group extension of the visual 01. So we are thinking about some pre-benchmark for the decision of GPU OFP2 and market. And this is a performance estimation of the hardware architecture. So we took some benchmark, and we had some benchmark competition in the by the GPU vendor. This is February to May in the last year. There are 7 benchmarks. One some of the CPU only code, and second group is if you have some GPU optimization code. And most of the interesting is some of the C and C++. The other thing is for kind of Fortran. So after the competition, so for the GPU for OFP2, that will be officially selected the NVIDIA GPU for OFP2. It decided last June, June 2022. So, of course, GPU for market must be the same architecture. So, what is the reason for the selection? One is the performance of benchmarks. The second thing is the ease of porting efforts. And third is the support environment, such as tool. And the fourth is important support. It's very critical. It is the 7 benchmark is good, but we have so many users of Fortran users. So four things is relatively very important. So that is because we selected some NVIDIA GPU. So we are, in this case, so we have started the porting activities. It's basically porting for users themselves. That's the basic policy. However, so we made it is really difficult to some big codes by own users. So we started the special support for big users group and community-wide providers. So we selected 16 groups. Each time we had kernel optimization and something like that, and by JC, HPC, and NVIDIA support. And also we are making effort to support our users. This is a very open program. So if you are interested in please attend some users. We have some mini camp and tutorials, consultation every month, and also we provide some of our materials and portals and videos. Please use this GitHub page. And we are many thanks for the supporting by HPC and the MHR member. So actually, maybe kind of GPU node competition for the OFF2. It's around targeted over 100 we hope. And also, so how about the CPU GPU combination FPUs? One is Intel and AMD excited 86 and 64-bit node. It's coming H100 and successful connected by PCIe and also something. The other option is the NVIDIA Grace and H100 GPU, NVIDIA Grace Hopper. And also, some GPU direct feature is very important because GPU direct for RDMA for the MPI, and also we think that GPU direct storage. It's a direct file I/O between the GPU memory contents and the storage device. This is a kind of assumed CPU node computation interface, Intel and x86 based way, something like that. There are two CPU, it's balanced interconnect and also balance some of SSDs. And maybe because this is PCI and some this is some NVIDIA connected. And how about CPU only node and storage? So it is a relatively smaller CPU number of the CPU only node because it is to follow the OP6 users. And EFP, Oakforest-PACS, and some night landing system are very high bandwidth memory. MCD, it's a very important thing. And memory bandwidth is very important to think about, and large bandwidth is preferable. And there are several candidates. Intel Xeon CPU Max and some NVIDIA Grace and AMD EPIC Genoa and Genoa X. And also storage supported by NVMe SSD based performance capacity and supported from the one and connection. So we are thinking about some of our design for target option by using some JHP project. One is I'm going to talk about some detail about there are two kind of things. So study on the next generation of data and it by the IO, and next topics practical acceleration methods to achieve high performance for large scale applications. This is provided by Mukabe. As the first one is led by some Professor Hanawa. It's an accelerator JHP project. We are now going to some project to accelerate this kind of stuff. So finally, I took some with a mark with it. It's a GPU cluster with 16 each 100 GPUs and prototype system of the Oakforest-PACS. So operation will start maybe we start schedule in November. This is November, and this is in operation by Nippon Comsys. It's a Xeon Platinum 4868 and maybe a Sapphire Rabbit 48 core, and such kind of DDR memory 512 gigabyte, and NVIDIA maybe NVIDIA H100 SX5 by 4, maybe 4 H100. It's manufactured there, and also NVIDIA Infinite NVIDIA plus maybe 400G inside. It's a connection that 4 nodes. It is also includes the 4 GPU and also connected by InfiniBand, but also connected via 100 gigabit Ethernet and connect via Ethernet Level 1. It's a summary of our talk. So I talk some brief overview of current status of Oakforest-PACS and its design procurement the starting operation at January 2025. It's a long-term installation phase. The current status request proposal. We hope some target 100 petaflops GPU node and GPU only node. But CPU nodes are but relatively so number, we assume. And it's designed and developed as a leading machine as a second class of PCIe next gen and PUGAC. It's advanced design with application is very important. And some we are continuing to promote the GPU porting of this application using with macro. And that's all. So it's fine. It's almost around 20 users total attending. So thank you for attending this seminar. We hope it's very good for your research views. So thank you for attending. So thank you for everyone to attend. Thank you very much. So it's the end of seminar. So let's end. Thank you very much.